All right, any questions? You guys have a question? No? Someone came to me and I had a question about the project that I said ask it in class. Yes. Okay, so this Wednesday you do what you've always done. You keep at your you keep at it, and so if we look at what I said should be the goals. So for this last week here, I want to make sure that all the issues that you now know what it is that needs to work by next Tuesday. So the demos are next Tuesday and next Thursday. Everyone needs to be ready by next Tuesday because I'm going to randomly choose who gets to present what. I'm just going to draw lots or something because it would not be fair if some people had an extra 2 days to complete. So by next Monday night, everything is done. But what I'm assuming now is that you're now far enough in your project that you know all the issues that are still remaining. And so I want to make sure that those are all there. So my hope, although that may be no more than my hope, is that everything is working except for minor bugs. With some of you that may be true, with some of you that may not be true, but that's my hope. So I'm also hoping that the documentation is substantially complete, so that whatever design documentation that you have, that's it. That's true or not, I'll find out. And as always, I am hoping that there is an even distribution of labor, and that every team member has multiple commits. So sometimes I see this project where like someone only commits like once a week, and that really is not what it's about. And of course, keep those status page. So I think everyone did start a status page, so that's good. So keep that status page honest. Write on it what is working and what is not working, and so that I know and so that you know. And of course, your individual reports, keep those up to date. I didn't give feedback on them last time, but they're there, and you should just keep them updated. And so then you're going to have a short week. That's why I say week 6 2/3, because it's about 5 days. 5 days long, where you can do whatever cleanup you need to do so that you have a successful demo next Tuesday or Thursday. So fix whatever remaining bugs there are, clean up the documentation, and make a presentation. So at some point there was a discussion on Piazza what I want to see in the presentation, but let me say it one more time. So there's three things that I'll be looking at. One is, did you produce something that works? Right? It always happens that it may happen that some of you it just never actually worked, and that's of course not a lot to show for 6 weeks. So it has to do something. Does it have to be the most polished thing ever? Of course not, right? We only had 6 weeks or so to do it. So what I want to see is that some interesting key mechanism or key something works well, and I want to have some idea as to how much of it is working. When you give those demos, focus on those interesting things. Something that's that you're later going to talk about when you talk about the design part. There's no need. The demo is not like an inquisition. You don't have to show off how every menu option works. There's sometimes people who say, "Well, let me show you how it can load files," and then they do just to demonstrate the file open box. That probably is not a good use of your demo time. So focus on the things that are most interesting to demo, and stay away from the ones that are dangerous to demo. And that's different for every project. So you need to make a decision. You only have a few minutes for the demo, and so use those few minutes wisely. And again, it is not your job to show me every last thing of your application in demo. That can get really gruesome. Then there's two questions that I want to know. Did this project teach you something about design? And that you can answer by telling me which part of the course you put to use to make this project happen. And some of you already approached me and said, I've been using this design pattern, I've been using these concepts, and if that happened, then that's great. Then you can report about that. And otherwise, think a little bit about where was some of the material in this course helpful. If you can't think of any, just lie and come up with something. So put what you've done in the project in relationship to the course material. And the third thing I want to know is, what was your experience, good or bad, with the teamwork? For many of you, this was the first team project. And it's always a difficult transition to go from individual projects to team projects. No one likes it. It's so much simpler to just work all by yourself. But the reason that you have to learn to work in teams is that just about anything that's worth doing is so large that you couldn't do it on your own. You have to know how to do the teamwork part. So tell me what worked well with the tools that you were using. What strategies did you use to keep everyone on board, if in fact that's what you managed to do? Or if things really went very poorly, just candidly say some of the things that didn't work, and then tell me what could you do better next time. There's no point in saying, well, this team member was a whatever negative attribute, and that's why it all fell apart. Next time, you may again work with someone who's not exactly the person you want to work with. But what can one do as a team to make that a little better? So that would be a more positive way of addressing issues like that. So the three things is, demo the cool parts of your project, tell me what you've learned or what you found useful from the material of the course when doing the project, and reflect on your teamwork experience. Those are the three things that you should do in your presentation. You have at most like 12 minutes or so for the presentation, because we need to get 8 presentations through in 2 days. And so with back and forth and questions, and so you should figure 12 minutes. So 4 minutes for each of those 3 parts would be great. When you give the presentations, give me the presentation slides in advance. That way it's an easy matter for me to just run these things on this machine. With a demo, in terms of not having to switch the display all the time and suffering through that, it would be really good if one can give as much as possible on this machine. With those of you who have to run servers and stuff, that might be, you might just have to line up three laptops here, because I don't know how else we're going to. Well, you know what? We could actually do that with the server people. We have 2 projectors, so we'll figure that out. But the more we can do on this, the better. So in order to facilitate that, and also in order to make sure that you have that useful skill, I want the presentation slides with some HTML-based slide service, not PowerPoint. PowerPoint claims to generate HTML. Don't even try. So don't bother with the HTML export from PowerPoint. Use one of those things that people use nowadays, where you just type in HTML. And if you want boring, you can use the one that I use, the HTML slide. It's dead simple. You just add one JavaScript and one CSS file, and then you just, it makes a slide at every H1. If you want snazzier things, I've given you a couple of suggestions, and there's a dozen of them that you can Google for, that give you like the transitions that are like what you use from PowerPoint, where they look nicer. I've given you one that on Piazza, one link to something that uses Markdown, because you're already familiar with Markdown from the wikis, and so that's again very easy. The reason I want you to learn this is because to put together a presentation with PowerPoint is, when people are moving away from it, A, it is time consuming, because to get everything arranged just so is tedious. B, it's not easy to share. What are you going to do with it? You're going to email someone some PowerPoint presentation? If I had $1 every time that I got a message for saying, are we looking at the same version of this presentation? Then I could retire. So whereas with the web thing, you just put them on the web. And the other thing is, it's just, you are going to have to produce a lot of presentations in your life. The easier it is for you to make a presentation, the less you have to do to bang one out, the better it is. So I can make a presentation with an HTML-based tool in 15 minutes. And in PowerPoint, there's no way that I would be having that kind of productivity. And so that's why programmers tend to do this time and these days. And I want to make sure that you know that. All right. So in fact, that's all I have. Any questions about this? Do you know what you need to do by this Wednesday and by next Monday? Oh, but it's tracers. What?
Oh, about this Wednesday, I was just a little bit late, so I can. Oh.
Yeah. So all it's whatever it says here, week 6 goes. So that's for tomorrow night, right? So I will check this out one more time, and I may or may not have time to give you your status update. I'll try. But and then the important thing is, on Monday night, be sure to check this in. The very first thing on Tuesday morning when I wake up, I will make that final update of all of the repos, and that's what's going to be on my computer for your presentation. So that's not a lot of time. Yeah. So, is there a possibility of an extension? No. Right? You have to give your presentations. So I don't want anyone to come and say, well, can I have an extra 2 days because my presentation is on Thursday. That would not be fair to those who present on Tuesday. So no more changes after Tuesday. Okay? And keep in mind, it is what it is. You don't have to submit the perfect project. At this point, shore it up so that some interesting stuff works, and that you can give a presentation that talks about what does this have to do with object-oriented design, and what was the experience with teamwork. That's all. Okay, if you can win in those 3 things, get something non-trivial to work, related to the course, and talk about teamwork, then that's what we're after. So I hope that's an attainable goal for everyone. Any final questions? Just ask again on Piazza. All right, then let's get going with the lecture. So we're talking about race conditions. We had this example where we had a bunch of threads updating a shared counter, and something went very wrong. And so now I'm going to show you a somewhat different example that's a little bit more sophisticated, and also something that's going to go very wrong. And then we'll talk about what one can do about these things. So in chapters 3 and 8, there was this ongoing example of a bounded queue, just a queue class where you can insert and remove elements, and it has a finite size. And so we have producer threads in this example that insert something into the queue. Here they're just going to insert a greeting, hello and goodbye. That's not a super realistic example, but queues are often used when you have concurrent programs, because they're a good way of splitting up your computation so that some of the tasks produce something, and then whenever they're done, they put it in this queue. And other tasks, that are able to change those results in some other way, then they take them out and work on them, and maybe then they put their work output in yet another queue. It's an easy way of organizing work so that everyone has something to do. But in this case, we're just going to have a dummy example where the producer thread inserts grading, the consumer thread removes greetings, and we're going to make sure that the queue is large enough so that we don't have to worry about the thread blocking when the queue is full. So the producer thread simply calls queue.add greeting on some greeting. And it keeps doing that. The consumer thread removes the greeting, and then it checks there's one of them is hello and the other one is goodbye. Then it checks whether it's a hello, and if so, it increments one count, and if it's goodbye, it increments another count. And at the beginning, it says it's seen each of those count one times and count two times. So in the main method, here we set up our bounded queue. We're giving it a size that's large enough, so we have 1,000 threads coming in. We're giving it 2,000 here. We're then setting up the executor service in the usual way. In this case, as a cache thread pool. We are now having 3 runnables, 2 for the producers and 1 for the consumer. And then we run them all. So what we expect when the consumer gets to 1,000 hellos and 1,000 goodbyes, that it'll eventually have extracted them all, and that it then will tell me that it got 1,000 hellos and 1,000 goodbyes. So that's what we expect. When you actually run this example, and in the interest of time, I'm not running it, you'll get the same effect as the one that you had in the lab on last week, that the numbers are just wrong. So it might happen that it says there's only 487 hellos and 807. So the question is, where'd they go? So I should call these A, B, C, and D. So let me set up this clicker question here, if I can, and then you can ponder while I'm doing this, you can read through the code on the slides and have a guess which of these things might be the reason. I don't know which lecture this is, but I guess here it should say that producers weren't able to insert 2,000 greetings into the queue because the program terminated before they were done. Three votes. All right. 10 votes. Could I have a few more? So let's have a look at a couple of things here. Could the queue have filled up? Yes or no? Why not? What's that? It did, right? Because if you look at the code here, it had 2,000 element space, and we're putting in 1,000 hellos and 1,000 goodbyes. So it had exactly enough space, and so it couldn't have been that it filled up and something got lost because of that. Could it be that the program terminated before either the producers or the consumers were done? Well, let's see. When does this program terminate? So what the main method does, the main method calls execute, 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 and shutdown. So the main method actually terminates pretty quickly. The main method is done before these various threads are done. Right? Because the execute doesn't wait for the submission to be complete. It just kicks it off. So it kicks off. Then it calls shutdown. What does shutdown do? Does it like kill everything right away, or does it wait until everything is done? It really does wait for orderly shutdown. So what shutdown does is it tells the thread pool that we're not going to submit anything anymore. So as soon as whatever has been running has completed, then you can kill the threads. And at that point, then the virtual machine will shut down. So shutdown does not terminate anything that's in progress. It just is an indication that nothing more will be added. So after these three tasks have all returned, then everything will be good enough. So let's look at these tasks again. These guys here, they just run something 4,000 times and then they're done. So that will surely happen. So they will add in 2,000 elements. Let's look at the consumer. There's a repetitions here. Is it only going to take out 1,000 things? Let's see where this number comes in. But no, over here it gets passed 2 times in. So it really does 2,000 repetitions. Otherwise, we would have expected to see some two numbers that add up to exactly 1,000. And we didn't see that, right? These two numbers don't add up to exactly 1,000. So this task here does do 2,000 things. And they all have to be either hello or goodbye. So it's still a mystery of what happens. It really does come to a conclusion. And so the correct answer must have been something else. So, and that was the majority answer by 35% of the votes. So, what is the something else? So let's see how this queue works. And so when you insert something into a queue, then one executes a statement like this. And after that, there could be a statement tail plus plus. But let's say that the tail plus plus didn't happen at the first insertion. But that thread, for whatever reason, now lost control The second thread comes in, and it also inserts something. So the way the queue is designed is that there is a pointer that always points to the last, to the next insertion location. That's called the tail. So you insert something here, and then you increment it. And so when you call insert or add, I guess it's add, then they're going to stack up. At some point, the tail reaches the top, and then it wraps around to 0. It's the circular queue that you're familiar with. Now, this is exactly the kind of thing that is super sensitive when you have more than one thread trying to do this at the same time. So if you have two that do it at exactly the same time, then the first one succeeds in the insertion, but say it has not yet So the first one here has inserted into here, and the tail is here. And now it loses control, and now the second one comes in. It now, because tail hasn't yet moved, it's going to just overwrite the thing here. And then it's going to increment the tail so that it now points here. Eventually, the first thread will regain control. It will regain control, and it too will call tail plus plus, so that now tail points here. And then some other thread, maybe this one or another one, will insert something in. So you can see here there's kind of a hole in here where nothing ever was written. So one value got lost, and this one here is going to be neither of the two, and that's why the counts are lower than expected. Now, clearly this is going to happen with every kind of data structure that you can imagine. Linked list, hash table, all of those things. When you insert something into one of those, there's more than one thing that needs to happen at one time. You need to make a new link, put something into there, move some next pointers, all of that exciting stuff that you've learned in your data structures course is going to be fragile when more than one thread works at the same time. So what to do about it? There are two solutions to this. And the first solution is not to try, but instead look into the standard library and see if they have a data structure that's thread safe. And in fact, there is one in the Java standard library called a blocking queue. And so for all practical purposes, whenever you're faced with a situation that you have multiple threads that need to insert something into a shared data structure, you should run to Java util concurrent and find some appropriate data structure. You should not try to develop your own at home. Don't try it. It's very difficult to do it right. But I will show you for a few minutes on how you would do it if you had to do it, so that you know what goes on under the hood and what those people who do this professionally, what tools they have. But I want to be very clear about this, because what normally happens is that students, they've had a lecture or two on how to write locks. And then they think that that's what they are also supposed to do. And I would think there's no one in this room, myself included, who should ever write anything with explicit locks. At best, we're going to do a bad job, and at worst, we can write programs that seriously misbehave. All right, but having said that, now let's see how these locks work. So lock is an object that has methods to acquire the lock and to release the lock. When you acquire the lock, or when a thread acquires a lock, then that's fine. Just now, the method to acquire the lock has succeeded, and the thread continues. But if another thread has already done that, And now the first thread says, I want to acquire that lock. Then it blocks. Then that thread cannot progress because the lock has already been locked by someone else. So the vision that you're supposed to have is, I have a picture here, is the old-fashioned telephone booth. So if you, there's already a thread in here that has acquired the lock. And so when you now try to call the method, whatever it is, to acquire the lock, then it's just not going to work, and you're just going to have to wait there outside for that person to be done. So when the thread inside is done, it's going to call a different method, unlock, and then you're going to have to try again, and then you will succeed at some point in acquire. Then your call to acquire will work. So there's two ways in Java on how to do that. Today we're going to be covering the one that uses the Java util concurrent lock interface, because that one is easier to understand. So we make ourselves an object of this type lock, and there is a class called reentrant lock for reasons that I won't discuss right this minute. We'll do that first. So we make somewhere an object of this lock class. That should be an instance variable of the data structure, in our case, the queue. Then here's the code that goes on inside the add method. The lock method tries to acquire the lock. Yeah. It does not automatically do anything to the data structure. So you have to. So people have always notions that locking does something intelligent, and it doesn't. It's a very primitive operation. When you call lock on an object of type reentrant lock, then all that has happened is you've called the lock method. One of two things will happen. Either you proceed right away, and that is if it happened that no one else had locked this object, not the whole data, just this object. Or you call lock and you just get blocked. You don't even know which of the two things has happened. So you just call lock, and so it's kind of like you're here and you grab onto the handle, and one of two things happens. Either you're now frozen in time, or you just smoothly open the handle and go. But you have no way of looking inside even. So here we see that we shouldn't be pulling the handle. But when you call lock, you don't know. So you call lock, and now you're at the hand of fate. Either you get to pass or you get suspended for a while. If you get to pass, then you can do whatever it is that you want to do. Oops, I'm in the wrong slide here. Then you do whatever it is. You insert something into the queue, you update some counter, and you can be assured that no one else can execute this code at the same time on. Well, the reason you can be assured, let's be clear why you can be assured, because anyone else who was also in this method here would have had to get past this point, and they can't. It's not because of any other magic, it is because this line here of code makes it so that no one else can proceed. That means that you have to be fiendishly clever about this, that in every other method that also might be messing with the contents of that data structure, you also need to put a lock.lock before what's called this critical section. And you have to use the exact same reentrant lock. It's an easy beginner's error where they put different locks for different sections. And that would not work. Yeah?
Would you put the lock inside the runnable itself?
No, you put it because if suppose you have two different queues, then each of them should have its own lock, so that all of the operations of the first queue are protected together, and all of the operations of the second queue are protected together. But there's no reason to share the lock between the two. So you want to use as little locking as possible. You could have a lock for a single lock in the entire program for everything, but then you unnecessarily restrict threads from making progress. So you want to figure out, and that's why it's hard. You want to figure out what is the minimal locking arrangement that you can get away with. In the case for the bounded queue, it's quite simple. So every queue object has a lock object. That lock object is used for all methods of that queue.
Should this be static?
No, it should exactly not be static, because you could have two different queues, and there's no reason why to block in the second queue when you insert something into the first. That's not a dangerous situation. So your program will run when it's static, but it might run slowly or it might deadlock because it might mean that no work can go on. So, of course, you have to unlock the lock at some point so that other threads can progress, and that's what the unlock method does. So that's like leaving the phone. As soon as one thread calls unlock, if others have called lock, one of them is allowed to proceed, and then they don't even know what happened is they unfreeze, and they just go on to the next instruction.
So everything between lock and unlock is protected.
That's correct. So that's this protected code. It's often called a critical section. So anything that critically must happen together is so. What you know is once you get to this point here, then you know that no one is going to interrupt you until you get to this point. And so that promise of no interruption means that you can do complex rearrangements, such as storing an element and incrementing a counter, or whatever it is, establishing links that need to happen together. So all of the stuff inside now happens together.
Should I always use try?
Yes, you should always use try finally, because imagine you don't use try finally, and this code here, for whatever reason, throws an exception. If this were to throw an exception and you didn't have a finally here, if you simply had protected code and then the unlock, then the exception would go from here to wherever, to the caller, and your lock would stay locked. It is kind of as if she had a heart attack, right? And the phone booth would not be unlocked. What would happen to everyone else? They would all be queuing outside, right? They could never enter. And so very likely your program then would just come to a halt. So that it's crucially important that you do the try finally thing. And now you could say if this code is so simple that it can never throw any exception, you could omit the try finally. That's of course true. People tend to put the try finally anyway because code that was simple at one point, can get less simple later. Yes.
So you lock. So here, I assume where you're creating the object, that's where something like the main method where you're manipulating the object. But the methods itself, they have a lock as well. So like I saw the add method, we had the dot lock here.
All right. So let's see if I have a complete. Let's look at the complete code. I must have it somewhere. I have to. I'm going to put this up and then go to the previous one. So here's the bounded queue, and it has some other condition stuff that we're going to be talking about later. So over here you see this is a class bounded queue. It has a bunch of instance variables. It has here the array of slots. It has the head and tail and the size. And then it has also a lock. So each queue has its own lock. And then when you look at a method, here's the add method. It locks and unlocks. And the remove method does the same. It locks and unlocks on the same lock. Because you don't want one thread to add while the other is removing. A similar chaos can happen. This way we know that at any time, this code here and this code here is protected and that it can only be executed by one thread. Yeah?
When the other threads hit the lock, do they then execute in a first come, first served?
That's kind of up to you shouldn't really rely on that. So when another thread calls this method and is blocked, you don't really know which one gets control. There is a way of making the locks so that they're quote-unquote fair, but it's expensive. And so it's not commonly done. Generally, you want to structure your application so it really doesn't matter.
So what if we set the priority?
You do not want to set the priorities. It's platform dependent, and so generally, it's certainly not something that an application programmer should ever do. So locks aren't good enough to do actual work, and here's the problem that you run into with locks. So let's say I want to, I have already made it so that add and remove are protected with a lock, and now I want to make it so that the queue, when you add to it, that the add method blocks if the queue is full. That's something you commonly want to do. So someone says queue.add, and at that point the caller of queue.add, if the queue is full, just will simply block until someone else has called remove. How can we implement that? Well, so let's try to make such an add method. We lock the queue, as we do. Then we make a test and say, is the queue full? And if the queue is full, then we're just going to be waiting. Except if we wait after having acquired the lock, no one else can acquire the lock to empty out the queue a little bit. And so then that would mean that the next one who wants to empty it is going to be sitting at another call to queuelock.lock, which they can't proceed against because we're still inside. So there's a problem with checking for fullness or emptiness while holding the lock. So to overcome that, there is another concept called a condition object. You can ask a lock and say, give me a condition object. And so here I'm making one that I call the space available condition. You can name it anything you want. And now inside here, remember there was a call to lock. Now I'm going to call on the condition object the await method. Await is a kind of a backdoor exit where I can say, okay, now I'm willing to kind of temporarily relinquish the lock. And so you can imagine what happens over here. If this lady here calls await, then she kind of vanishes somewhere into outer space, and someone else can temporarily use the phone. And that's kind of solves the immediate problem. Now someone else can do their work to empty out the queue a little bit. But the question is, how does the lady ever get back in? And the answer to that is that some other thread, and then in our situation, that's the one that does the removal, has to signal with this method called signal all that now the situation has changed, and whoever was calling await on the space available condition gets a chance to get back into play. So now let's visualize here the phone booth again. So this lady has called await. She's now in outer space, just waiting. Someone else has gotten into the phone booth, has done something, has unlocked it again, and now calls signal all. And now maybe the lady gets put right back in and she keeps going where she was before. Maybe some other thread actually beat her to it and snuck in and did some other work, and then she has to wait a little longer. But signal all means that she is now ready to compete again to get back in together with the other threads. So one of them will get back in. Maybe it's her. So, yeah?
Does the signal all also lock it again?
No. No, the signal all just, it kind of unfreezes the ones who are in outer space. It just puts them back on planet Earth, but not quite inside. So then she's just standing outside competing with everyone else. Yeah?
So let's say there's somebody who's trying to add but it's full, and then that person calls the waiter, right?
Yeah.
If let's say there's two other threads waiting, another add thread, another
Yeah.
thread, it's possible that the add thread could go in and also wait.
Oh yes, there could be more than one in outer space.
And it would keep going until like the remove comes.
Right.
And then signals them all to the start.
Yes, and then signal all means that all of the ones who had been waiting get woken up. There is a signal that says only one of them gets woken up, and there's some situations where then that's the wrong one. So the advice for beginners is to always use signal.
So then so it'll just keep happening or it'll keep going until the space is
Yeah, absolutely.
Also use
No.
But so if the set the signal out, so they will also give up the lock.
They have given up the lock. Everyone who's called await, has given up the lock.
But you said that's temporary. Why this is temporary?
Well, meaning that that when okay, so I guess the difference is that okay, I understand. I think I understand your question. So let me try to say it like this. Let me actually look at the full code. It's a little easier from there. So let's look at that. So when you wait on this thing, when you wait on the lock, then you kind of stand at the entrance, and eventually you're going to just move on. This call will return, and you just keep on going. But when you are waiting on here, okay, no, so I know how to say this. When you're waiting on here, and you're given a chance to resume, then this call returns, but the lock has been reapplied to you. So even though you don't call lock, the lock is being given back to you. So that's why I say you temporarily relinquished it. Because otherwise it wouldn't work, right? You wake up inside here, and now you start messing with stuff. So if you didn't own the lock, then the guarantee of that this, because there's only one thread is in here, would be violated. So notice that it's critical that you put this in a while loop and not just an if statement, because it's possible that the queue is full and you wake up and you get back in and it's still full. Because someone might have added, someone removed, added, and so it might still be full. So you need to keep testing this until you know that it's no longer full, and then you get to progress and do your stuff. And you're now assured that there's at least one space available, because no one can interrupt you anymore. So that's a complex thing that requires some thinking through. So I've come up with another lab for it that hopefully will be helpful. I think it'll be the last lab of the semester. Yep. Okay. That was my lab. Okay. Let me see what happened to my lab, if I have it. Maybe it was lab 28. Nope. Yeah, it's only 2 slides, so I must have messed something up. Let me see if I have it on my other computer.